All right, today we're cracking open the playbook on industrial safety, and we're looking at a big one, API 521. This is the critical engineering standard, the blueprint, that designs layers of protection into chemical plants and refineries, all to prevent the absolute worst-case scenario.
So let's just start with the biggest question on the table, right? What is it that actually keeps a massive, high-pressure industrial facility from becoming a bomb? Well, the answer lies in identifying, understanding, and then actively managing one very specific and very immense danger.
And that danger is overpressure. It's a simple concept, really. Every single piece of equipment, from a tiny pipe to a giant reactor, has a maximum pressure it can safely handle. If you go over that limit, you risk a catastrophic failure, a rupture. Simple idea, but with incredibly complex and dangerous implications. Now, to manage this, engineers first have to map out every single potential threat. And that brings us to our first section, really understanding the unseen danger. This slide gets right to a core philosophy of safety engineering, single jeopardy. The idea is that systems are designed to handle one credible, unrelated thing going wrong at a time. The standard is really clear on this. You don't have to design for double jeopardy, two completely unrelated things failing at the exact same time. It's just considered too unlikely. And that right there draws a fundamental line in the sand for what engineers have to prepare for. So what are these single jeopardy events we're talking about? Well, the list is pretty long and covers a huge range of problems. You could have an external fire literally boiling the contents of a tank. An operator could accidentally block an outlet pipe. A critical control system could fail. You could even have a chemical reaction that just spirals out of control. Heck, even liquid trapped in a pipe that's just sitting in the sun can expand and cause overpressure. Every single one of these scenarios has to be analyzed, and each one needs its own protection plan. But, some dangers are way more sudden and violent than just a slow pressure buildup. The standard calls out a particularly terrifying scenario, what's called a superheat limit explosion. This can happen when a really volatile liquid, like water, suddenly comes into contact with a much, much hotter fluid, one that's above the water's own boiling point. And the result? Well, the standard itself says it's analogous to a detonation. The key thing to understand here is this isn't just boiling. We're talking about an explosive flash of liquid to vapor that happens in microseconds. A standard pressure relief valve? Totally useless here. It's just way too slow. And this really highlights why you can't just react to overpressure. Some scenarios have to be prevented from ever happening in the first place. So if those are the dangers, how do we actually engineer systems to handle them? Well, that brings us right to our next section, the path to safety. This shows the classic engineered escape route. It's brilliant, really. When a vessel starts to overpressure, step 1, a pressure relief device, or a PRD, pops open. Step 2, all that high-pressure fluid gets funneled into a big network of pipes called a collection header. From there, step 3, it flows into a knockout drum, which is designed to separate out any liquids. And finally, step 4, the leftover vapors are sent to a flare stack to be burned off safely. Let's zoom in on that knockout drum for a second, because its job is absolutely vital. You just cannot have big slugs of flammable liquid getting carried all the way to the flare tip. That's how you get what they call raining fire. So this vessel is designed to slow everything down, letting the heavier liquids drop out by gravity, so only clean vapor continues onto the flare. But here's the thing. Even this safe disposal has its own hazards. A flare can kick out an enormous amount of heat, thermal radiation. The standard gives guidance on how to limit people's exposure to this. And a really common industry practice is to block off any areas where that radiation could exceed 6.31 kilowatts per square meter. It's just a constant reminder that every single part of a safety system needs its own safety analysis. So this entire system we just looked at is reactive, right? It only kicks in after a problem has already started. But what if you could prevent the problem entirely? That brings us to a more modern approach to safety, one that's all about being smarter than a valve. And this is it, a high-integrity protection system, or HIPS. Now, this isn't just one device, it's a whole system. You've got sensors, a computer, what they call a logic solver, and final elements like super-fast automated valves. Its entire purpose is to spot the very beginning of a problem and automatically take action to stop it, long before overpressure even becomes a threat. This slide just lays out the difference in philosophy perfectly. A traditional pressure relief device is reactive. It only acts once the emergency is already happening. A HIPS, on the other hand, is preventative. It sees the problem coming.
and removes the source. Maybe it shuts down a pump or slams a valve shut before the pressure even gets a chance to build up.
And the reliability of these systems isn't just a guess. It is rigorously defined and calculated. They're classified by safety integrity levels, or SIL. And as you can see here, the higher the SIL number, the more reliable the system has to be. A SIL 3 system, for instance, has to be proven to work between 99.9 and 99.99% of the time it's called upon. We're talking about serious, quantifiable, high-stakes engineering.
Okay, so let's pull all these different ideas together now and look at the big picture philosophy behind API 521. Because at the end of the day, it all comes down to building the layers of protection.
You know, the key takeaway here is that API 521 isn't just a collection of rules. It's a framework for systematic, critical thinking. It forces engineers to think about and anticipate every credible failure they can imagine. It makes them build multiple, independent layers of protection so that one failure doesn't spiral into a catastrophe. It ensures there's a well-engineered, safe path for disposal when relief is absolutely necessary. And more, it's pushing the entire industry to evolve, to shift from just reacting to problems to actively preventing them.
This final quote, I think, just perfectly captures how deep this thinking goes. When you're analyzing a scenario like a tank overfilling with liquid, the standard requires you to validate the entire system, right down to the concrete foundation it's sitting on. You have to ask the question, can the foundation even support the massive weight of a completely full vessel? It's the ultimate example of thinking about a problem from end to end. Which leaves us with a final and pretty challenging thought. This entire framework of safety is built on our ability to anticipate credible failures. But as our industrial systems get more and more complex, more interconnected, more automated, does that challenge of anticipating every single potential failure path eventually become insurmountably difficult? It's something to think about.